Hi and welcome to Lab 7. In this lab, we are going to learn how to build latches and flip-flops in VHDL. So we are going to take a quick recap of latches and flip-flops and the differences, and then we are going to see how to write behavioral descriptions for these elements in VHDL. So let's begin. So a latch is an element that can store 1 bit of data, and it is level sensitive. So a typical D-Latch, for example, has the inputs D and clock. Sometimes this input is also called enable and an output Q, and it is sensitive to the level of the clock signal. So whenever the clock signal is high, Q is equal to D, and as soon as clock goes low, the older value of Q is retained. It does not change even if D changes. Such a D-Latch is called positive level sensitive D-Latch. That means when enable or clock signal is high, that is its level is high, the latch is transparent. And when the clock goes low, then Q retains its old value. On the other hand, a negative level sensitive D-Latch, often indicated by a bubble here to indicate an active low clock or enable signal, is a latch where the latch is transparent when the clock is low. Whenever the clock is 0, Q follows D, and when clock goes high, Q retains its old value. Coming to a flip-flop can also store 1 bit of information, but it is edge sensitive. Okay, so that means the state of the flip-flop is updated on the edge of the clock. The symbol for a D flip-flop is very similar to that of a latch, except this little wedge shaped symbol on the clock, which indicates that this is a flip-flop. A little wedge occurring on the clock indicates the flip-flop, and this is a symbol for a positive edge triggered D flip-flop. That means on the rising edge of clock, when the clock is going from low to high, whatever was the value of D, suppose it was 1, is stored in Q. So if Q was low here, then upon this clock edge the value of D is sampled and is reflected in Q, and subsequently until the next rising edge occurs, this value remains as it is. Then on the next rising edge, again the value of D is sampled. So suppose the value of D was 0 at this point, then that value is stored in Q. So that is the behavior of a rising edge triggered D flip-flop. Similarly, a falling edge triggered D flip-flop is similar to the rising edge triggered, except the value of D is sampled on the falling edge of the clock. So on the falling edge, that is when clock goes from 1 to 0, the value of D is sampled and stored in Q. So how do we model this behavior in VHDL? So first of all, as was covered in the lectures before, a D-Latch can be built using logic gates in this manner. So let's say you need to have a feedback loop to store the value. So we have 2 NAND gates connected back to back like this. This will be our Q and Q bar. Okay. Then we have another set of NAND gates, one input of which is connected to clock and the other input is connected. So if these inputs were not connected, this would be like a S bar R bar latch, but if we connect them like this, sorry, this would be an SR latch, not S bar R bar, it will be a SR latch. But now when we connect the inputs together using an inverter, then we get a D latch. So this is the logic diagram for a D latch. So in this lab we are going to focus on behavioral descriptions. We are not going to discuss the structural description of a D latch or a flip-flop, which you may already know can be built using these kind of logic gates. And so this is a D latch. Similarly, using a single D latch like this and creating 2 instances of this description, you can build a master slave D flip-flop. So a D flip-flop can also be constructed using basic logic gates using structural VHDL. Coming to behavioral description, that means how do we describe these latches and flip-flops using the process construct in VHDL. So let's do a quick recap of the process block. If you recall, process block, so inside the architecture there are a set of concurrent statements. Those statements are concurrent, they exist simultaneously, and process block can be one such concurrent statement. The entire process block acts like one concurrent statement and it exists concurrently with these other statements. And a process block has a label and it has a sensitivity list. That means this process block is triggered when any of the signals mentioned in the sensitivity list change. So whenever, let's say in this example, the value of A or B changes, this process block is triggered and the statements inside it are executed in the sequential manner one after the other. And when it reaches the end, and this is instantaneous, like there is no delay that elapses, so these statements are executed in instantaneous time to compute what should be the final values that this process block should update. So for example, if this is the process block and the sensitivity list has signals A and B, and inside this is updating some signal Y. So whenever any value or any event occurs on A or B, any value changes, this is triggered. Then this is like a C code or a Python code to compute what should happen, and the computed value is then applied on the signals. So in this case, it is applied on the signal Y. Either a 1 or a 0 is applied. So this is the way a process block is executed. So sensitivity list is the list of signals on which if any change occurs, then the process should be triggered or evaluated. So the process is sensitive to these signals. Okay. Now notice that there can be other signals acting like an input here, but they may not appear in the process block. It's possible that, let's say a signal S, there is a 1 and a S, for example. A signal S appears inside the process block, but it is not there in the sensitivity list. What does that mean? It means that if the value of S changes also, it may or may not trigger this process. But if A or B changes and this process is triggered, then at that point of time, the value of S is read and used. So using this understanding of a process block, let's write the behavioral description of a D-latch. So our latch has the inputs D of type standard logic, clock of type standard logic, and a single output Q. So this is this interface, and the behavior of the D-latch is as follows. We use a process block, and in the sensitivity list we have clock and D. Okay, that means when any of these changes, it should reflect in the output immediately, because that's what we want. That's the behavior of the latch. So when clock is low, the old value of Q should be retained, but when clock is high, anytime there is a change on D, that should be immediately reflected in the output. So we use the if block within the process block. So if clock is 1, then Q follows D, and if. That's it. We don't have to say what otherwise. So obviously it is implied that if clock is 0, then nothing should be done. That means Q remains unchanged. There is no state change happening for Q. So this simple description gives us the behavior of a D-latch. Let's see the simulation results. So here are the simulation results of a D-latch. Let's see if it matches the expected behavior. So this is clock, okay, and this is the rising edge here. The rising edge is occurring here, here, and so on. Sorry. This is the rising edge on the clock. So at this point of time, the value on the first rising edge, the value of D is 1. So before that, Q was unknown, and that's why it appears as a X. So it was not initialized in the simulation, and therefore it appears as a X, unknown. At the clock edge, the value of D is sampled, okay, and that is 1, and then Q is exactly equal to D for the time duration for which the clock is high. So it is till this point that clock is 1, and therefore Q is equal to D. Then for this duration, clock is equal to 0, so Q retains its old value, which was 1, and so on. So this simulation results are as expected. So you might notice that D here is not exactly like a square wave, it is some unregular sort of a waveform, and we need to try out all possible combinations to actually test this circuit. So in the test bench, when you're writing a test bench, it's very important that you try all possible combinations, right? So when clock was 1, did D change? First of all, D has to change. We have to see if when the clock is 1, does D change or not. So the test bench has to test that. Secondly, when clock goes to 0, you should try whether if D was 1, it remains a 1, and whether if it was 0, it remains a 0. So those two combinations also have to be tried. So your test bench has to test or simulate all of these various aspects. So just having a square waveform appear at D might have not done the trick. So we need some sort of irregular waveform to appear at D, yet we don't want the clock and D to change at the same time, right? So we want the input to be stable a little before the clock changes. Well, not so much in the latch, but at least for the flip-flop. For the latch, it's all right. So let's see what are the simulations, what is the test bench to get this waveform for D. This is one way of doing it. You can think of other ways. So first of all, here is the test bench. Okay, this is the entity part, and this is the architecture part. And we have first declared the component for our D-Latch, and then we declared some signals. So here is clock, here is Q, and here are a bunch of signals D0, D1, D2, and so on. So why have we used this? Let's see. So initially we create a component for the D-Latch. We create a square waveform on clock of time period 20 nanoseconds. So clock reverses every 10 nanoseconds. So this period is 10 nanoseconds. Now we create another waveform on D0 with the time period 10 nanoseconds. So D0 looks like this. So this is also 10 nanoseconds, and the on or off period is 5 nanoseconds. And now we don't want this D or clock to change at the same time, right? Well, it should be okay, but ideally we don't want this to be a regular waveform like this. So we declare another signal D1, which is another square wave, and then we XOR the two to create a signal which is D2, which is some irregular waveform. And then D is a slightly delayed version of D2. So D is equal to D2, but shifted ahead in time by 3 nanoseconds. So this is one way of creating some irregular looking waveforms in VHDL. So let's see the same simulation, but with D0, D1, etc. printed out. Okay, so here is D0 and D1, and you can see that D is it's a XOR of the two shifted and shifted slightly. Okay, so now coming to a flip-flop. Okay, how do we write the behavioral description of a flip-flop? So the flip-flop has the same ports. It has the input port D and input port clock. Remember the little wedge to indicate that it's a flip-flop, and output Q. So we have the same ports as the D-Latch, and now we want the value of D to be sampled only on the rising edge of the clock and not otherwise. So even when clock is high, suppose D was 1 here, and then there is a little low going pulse here, the output should be sampled, the D should be sampled here and stored at the output, and it should retain that value until the next rising edge. So that is the behavior we want to describe in a flip-flop. Okay. Irrespective of D changing when the clock is high, that value that occurs only on the rising edge should be sampled and saved as Q. So this is how we describe the D flip-flop as in a process block. Notice that this is the sensitivity list and only clock appears in the sensitivity list. We don't need D in the sensitivity list. Okay. That means only when the clock changes do we evaluate this, and in between, even if D changes, the output or the state of this block, that is Q, remains unchanged. So even if D changes, Q remains unchanged. But when there is an edge on the clock, then we find the next state Q. We evaluate this. So this syntax here, clock tick event, indicates there is an edge on the clock. So if there is an edge on the clock, and if clock is 1, that means it's a rising edge. Then Q is assigned the value of T and end if, which means if this condition is not met, then Q retains its old value. It retains its old value, it is not changed. Similarly, if you wanted to describe a falling edge, how would you do it? If you wanted to describe a falling edge triggered flip-flop, you would say if clock tick event and clock equal to 0. Okay. So there was an event on clock and the new value of clock is 1, then this is what the statement means. Or if there was an event on clock, that means the value of the clock changed and the new value of clock was 0, then do something. So these two are ways of describing that you want to execute the statements here on the rising edge or a falling edge. So this is the behavior of a D flip-flop. Okay. Let's see the simulation results. Here are the simulation results. So we have clock, which is a regular square waveform of time period, I think 10 nanoseconds, and or is it 20 nanoseconds? Okay, let's see. It's a square waveform, and we have D, which is again this irregular sort of a waveform. Okay. So this is the rising edge of the clock. So at this point D was 1. So until that point Q had the value unknown and X. Okay. So till that point we had not initialized Q in the description. So it retained the value unknown. Then when the clock edge arrived, D was 1. So Q took the value 1 and retained that value. So notice that in this period clock is high and D changes but Q does not change. So the value that was read at this edge is retained throughout. It does not follow D in this period. And again for clock equal to 0, the value is retained until the next rising edge arrives, at which point the value of D was 0, so Q falls to 0, and so on and so forth. So the simulation results show that this behavior is as expected. This is what we wanted to describe. So how do we write the test bench for this? It's the same test bench. Okay. Now you may want to model a D flip-flop with a reset signal, and this is very useful. Similarly, you can have a flip-flop with a set input, but we'll just see, for example, a reset input. So this, let's see, this is a D flip-flop. It has an input D. Now this is a flip-flop, so it has this wedge-shaped symbol. It has a clock input. It has a Q output, and it has another input called reset. Okay. Now we want this reset to be synchronous. That means the value of the reset input should be sampled only on the clock edge. And because we have a positive edge triggered clock in this picture, it should be the value of reset should be sampled and should take effect only on the rising edge of the clock. So let's first see the simulation results and then let's see how to code this in VHDL. So essentially we added another input R. So initially R was 1, okay, but the value of R was not taken into effect until a rising edge of the clock. So here is an edge of the clock at this point, and here reset is 1. So at this point is where Q goes to 0. So at this point we have Q being 0. Before that Q was unknown. Now when Q goes low, okay, let's see if on any other rising edge, now the reset goes low here, so reset should not take priority. So what happens is reset should take priority. When reset is 1, irrespective of what is the value of D, Q should be 0. So even if D was 1, etc., it should be ignored. But if reset is 0, then the value of clock on the clock edge, the value of D should be assigned to Q. So let's see, here the reset goes low here, and on the clock edge, on this clock edge, we have D is 0, so it's not changing. Now on the next clock edge, that is here, we have D is 1, so therefore Q becomes 1 on this edge, and so on and so forth. So notice that at this point here there is another pulse on the reset input. However, this pulse does not coincide with the rising edge. So a rising edge occurs here and here. So here is a rising edge and here is a rising edge, but this pulse occurs somewhere in between. So it has no effect because this is a synchronous reset. So if the value of reset was 1 during the rising edge, only then would it have made any difference. So since this reset pulse occurs in between, it should have no difference. And that is what we see here in the simulation. So here, for example, on this edge, D is 1, so Q goes to 1. At this point, Q is 1. And then it remains a 1 until the next edge where D is 0, so Q becomes 0, and so on. And this reset going high in the middle had no effect. Now let's see how would you describe this in VHDL. Take a moment to think about it. So we have added a port called R, which is an input port, and in this process, okay, we again have only clock in the sensitivity list. Why do we not have reset? Think about it. Should you or should you not have reset in the sensitivity list? This is a synchronous reset. That means we ignore the values on reset unless there is a event on the clock, unless there is a edge on the clock signal. That is what is meant by synchronous. Therefore, we are changing any state, if at all, only on the clock edge. Therefore, we only have clock in the sensitivity list. We are not changing the state of anything if R changes, okay, unless it happens to be on the clock edge. So it's only the clock edge that we are looking at. So only clock is there in the sensitivity list. So if there is an event on the clock and if clock is 1, that means only on the rising edge, not on the falling edge. First we check for R. So recall now this fact that inside a process you interpret the statement sequentially, so you interpret them one after the other. So if this condition is met, that is reset is 1, then Q is assigned a 0, else Q is assigned D. So if reset was 1, then this part would never occur. Okay, so we interpret them in this one after the other manner, in the sequential manner. So if reset was 1, that's why reset is given a priority. If reset was 1, then definitely Q is equal to 0 irrespective of D. But if reset was 0, then you look at the value of D and assign it to Q. And all this happens only on the rising edge of the clock because of the statement. So we can nest if statement. So this is one if block, if end if, okay, and inside this there is a if, else and end if block. So you can nest one if block inside another if block. And finally, this if block is nested inside this if block, which is nested inside a process block, which is nested inside an architecture block. Okay, so this nesting is very useful and common in VHDL as it is in many other languages.